Before starting the design of a control structure, it is necessary to have some knowledge of the process. Well, first of all, you have to understand the underlying dynamics in the time domain, but also in the frequency domain. If you know the process in the frequency domain, it's a bonus. This is what we mean by process behavior knowledge. This section will review the main building blocks and will enable you to identify the process dynamics from its signature in the time domain, for example a step response, or from its signature in the frequency domain, for example a frequency response. Of course, process knowledge is much more than just knowing the process behavior. It is always a very good idea to understand, between quotes, the process and to have some insights behind the physics of the process, so that you, for instance, know how the process is interacting with other processes. To decide on the control structure, it is a good idea to have some awareness of the linearity of the process, the presence of disturbances, load disturbances, output disturbances, are these disturbances measured or not, and finally to have an idea of all the constraints that are imposed on the system. You will often see that a good discussion with the process engineer or with the operators will help you to acquire quite some process knowledge. The process has huge impact on process control. Well, first of all, on the control structure, as we will see in the next section. Let us take, for example, disturbances. Well, they have a serious impact on the controller structure. If you have, for instance, a load disturbance, well, cascade control can help you reject it if this cascade can be implemented. And for instance, if you have a disturbance on the output, well, then feed forward can be used. Of course, this disturbance needs to be measured. The process behavior, that is the underlying dynamics, has an impact on the controller type. If the dynamics of the process is first order, of course a PI controller is sufficient. But for instance, if you have a process with a substantial second time constant, well, then PID control can be interesting. Also, if there is a large dead time in the system with respect to the main time constant, well, then more complex control structure can be used, such as the Smith predictor or internal model control. The type of control problem, so disturbance rejection or tracking, this is also a form of process knowledge, has influence on the aggressiveness of the controller. So for instance, the controller will be more aggressive in a disturbance rejection case. If the process is nonlinear, you might have to adapt the controller tuning in function of the working point. This will lead to gain scheduling or simply scheduling. At the end of the course, you should be able to select the appropriate controller structure, the appropriate controller type, given your knowledge of the process. This means that at the end of the course, and especially at the time of the exam, you must have a mental picture of all the available controller structures and controller types with their associated area of application. We'll start this section on process behavior with a very important but rather simple concept, the concept of the process gain. Right? In order to obtain this process gain, what is usually done is to apply or impose a step at the input. Okay, and the input is mv, the manipulated value. So the increase will be delta mv over here. So what you're going to do is observe the response of the system, and of course, since the system is almost always dynamical, well, you'll have a response that could be this one. Well, the idea of a gain is really the ratio in steady state. So this means that the transients have disappeared because the system is dynamic. Well, after a while the transients will disappear and you'll have, after settling, a delta PV, right? And the process gain is really the ratio between this steady state increased delta PV over the delta MV that has been imposed, and will denote this gain as Kp, right? Kp as units, it's the units of PV divided by the units of NV. So let us take an example again from the paper industry, and we'll assume here that MV is the stock flow, right? And the stock flow is expressed in liters of stock per minute, right? And PV here will be the grammage, and this is expressed in grams per square meter. So if you do an experiment like that, an increase in stock flow, and you look at the resulting grammage increase in steady state, you can obtain the gain, and this gain is really expressed in grams per square meter per liter per minute, right? Well, the process very often is non-linear. So if you do that kind of experiment here around another operating point, well, you might have another result. For the paper process, we had seen that the operating point is dictated by the production line speed, right? And we'll assume here that this experiment has been performed at a speed of the machine of 600 meters per minute, right? And then we can say, well, what would happen if we do an experiment at 900 meters per minute? Well, we have already seen that the delay of the system will decrease. We have this distance between head box and scanner stays the same, but the speed is higher, so the dead time will be smaller, okay? But we have the same increase in stock flow, but the speed is higher. So this means that the delta PV in the second experiment will be smaller. So if we do the same experiment with the same delta MV, we'll probably have a response of this type, right? A smaller dead time. It could be also influences on the time constant, and it might look like this, right? So this is now my delta PV, and you can see here that around this second working point the gain of the system is smaller, and this is because of the fact that the system is indeed non-linear. Since the process gain has changed, well, it's kind of intuitive that we'll have to adapt the controller tuning, and this will be handled in the section on gain scheduling and simply scheduling. Many vendors of control systems work with a normalized control algorithm, and this means that, for instance, PV has to be normalized and expressed in percent of the measurement range, PV min, PV max. In our previous example, assume that the sensor that measures grammage measures in the range 0 gram per square meter, right, up to 200 grams per square meter. Then PV will be normalized in such a way that, well, 0 grams per square meter correspond to 0%, right? And that 200 grams per square meter corresponds to 100%. This is what you can see from this formula. So how does this normalized PID controller work? Well, you have the PID control algorithm, and it is working on the basis of PVN. You have something similar on SP, and here you have percent, right? So here you have this normalization, and what enters here is PV and SP, right? And here you have the PV units, right? And you have something similar here at the output. We'll see this in the next slide. We have MVN, right? And then you have to kind of denormalize to obtain the MV that has MV units, right? This one will also be expressed in percent. So this is the PID controller, right? PID control. But from a tuning point of view here, well, this PID controller sees a process from MV normalized in percent to a PVN that is normalized as well, right? So it is important to, when you tune this controller here, to take into account the normalized KP, right? And this normalized KP will come from an experiment just as before, and you'll have to use delta PV normalized over delta MVN. Okay, so this is why this normalized gain is important. And of course, the fact that you're working with this normalized process will involve also that you use here a normalized controller gain, and this we will see in the section devoted to PID control. The reasons why the vendors use a normalized PID control algorithm is that when you normalize things, well, KC normalized is in the neighborhood of 1, and this is why also this factory tuning that we talked about has a KC of 1, right? And the fact that you normalize will prevent KC from being very small or very large, because this could cause, well, numerical problems in the implementation of the PID controller. As we have seen in the previous explanation, MV is also often normalized, so it is expressed as a percentage, this time of the control range MV min, MV max. So if we take our example with the stock flow, it could be that MV min is 0 liter per minute and MV max maybe 1,000 liter per minute. So the normalized MV would be, of course, corresponding to 0 liters per minute, 0%, and 1,000 liter per minute would correspond to 100%. The output of the controller will produce the normalized MV, and you can obtain MV by turning this formula around, and this is then what you obtain. Well, there is an actuator that is often used, and it's the control valve, and there obviously MV min is 0%. This means that the valve is closed, and MV max is 100%, so the valve is open. So this actuator is kind of normalized naturally, so obviously MV and MVN are identical. The normalized gain of the process is defined as the ratio of the steady state increase of the normalized process value, delta PVN, over the increase in the normalized manipulated value, so that's delta MVN. And this gain here, this normalized gain, is expressed in percent over percent, so it's percent of the process value range divided by the percent of the manipulated range. And normally this normalized gain should be in the neighborhood of 1, and this is assuming that the actuator sizing has been done properly, that there are no nonlinear effects, and if there are nonlinear effects, that you work around an operating point where the actuator sizing has been done, right, and that the sensor measurement range has been chosen appropriately. A first reason why the normalized gain of the process might be substantially different from one are nonlinear effects, and these effects might cause the normalized gain to be substantially higher than 1 or substantially lower than 1. Let us have a look at the static, okay, this is very important, relation between the normalized MV, MVN, and the normalized PV, right? So here we have 100%, and here we have 100%, and well, if we assume that the system is linear, well, you would have that kind of behavior. So when MVN is increasing, you would have a proportional increase in PVN, right? Well, what might happen is, for instance, that the system is nonlinear, and I'm going to exaggerate things here, and that this static relation looks like this, right? If you do here, if you this point and you take the tangent here, you can see here that around this point, well, the normalized gain is approximately 1. So if you doing the actuator sizing around this point, well, you'll have a normalized gain of 1, right? But you see here that if you work around another working point, like here, well, the normalized gain might be substantially smaller than 1, whereas if you work around this working point here, the normalized gain might be substantially higher than 1. Well, this normalized gain, as I've said, is also influenced by the actuator sizing and the choice of the sensor measurement range. Let us take an example where the normalized gain KPN is much larger than 1. So for instance, KPN is equal to 2. What you can do is look at the historics of all your trends that you had during production. This can be done in the HMI, in the SCADA system, and you will see that MVN, the normalized manipulated value, is living in the range 0 to 50%. Because of this normalized gain of 2, obviously the normalized PV will live in the range 0 to 100%. Since all those trends cover your whole production, you can see here that the measurement range has been chosen appropriately, but you can see here that your actuator range is not okay, because you're only using 50% of your normalized actuator range. So it looks like the actuator is over dimensioned, right? It could be also that you're trying to go above 50%, but that this is not possible because your sensor measurement range is too small, but this is not very likely because production and management would intervene immediately to have the sensor replaced, as going above 50% would lead to an increase in production, right? So if you have a normalized gain that is substantially higher than 1 and it is not due to non-linear effects, it's probably due to an actuator that is over-dimensioned. Let us take an example of a KPN that is small or much smaller than 1. For example, KPN is equal to 0.5. Then again, you can go and have a look in the historics of all the trends, and if you see, for example, that MVN lives in the range 0 to 100%, so the actuator is dimensioned, all right. So the actuator sizing has been done properly. Well, because of this normalized gain 0.5, you will see that PVN, the normalized PV, will live in the range 0 to 50%, okay? And this means here that the sensor measurement range has been chosen too large. It could be also that you try to go above 100% normalized actuator range, but that you can't because the actuator is underdimensioned. But this is not very likely because production and probably management would intervene and call for a replacement of the actuator, because replacing the actuator would lead to more production. So if you see a normalized gain that is substantially smaller than 1 and it is not due to non-linear effects, it's probably due to a sensor measurement range that is too large. There is a link between the normalized gain and the unnormalized gain of the process. As we have just seen, the normalized gain is the normalized variation in PV at steady state divided by the normalized variation of the manipulated value, okay? Delta PVN is given over here and delta MVN is given over here. So these two will cancel out and this will lead to this expression, and of course this is here delta PV, the steady state variation, right, not normalized, over the variation of MV without this normalization. So here we have this link between KPN and KP, and well, the proportionality factor will of course involve the MV range and the PV range. This normalized gain, as I've said, is important because some vendors implement, as I've shown, a normalized PID controller. So it will be very important to use the tuning algorithms introduced in section 5 with the appropriate gain. If the algorithm, the PID algorithm, is normalized, you have to use the normalized process gain. If it is not, you have to use the standard process gain. Well, the next type of process behavior that we tackle is process delay or dead time. So here you have an example of a transporter belt or conveyor belt, and there is transport of material between point 1 and point 2. So W1 and W2 here are linked simply by this relation over here, right? There is a delay in between W and W1. This delay can simply be computed over here. Well, it's the distance that has to be covered, and this is in meters, of course, divided by speed, and of course this leads to a delay, and of course it has units seconds, right? You can see here that this delay is throughput dependent, so it depends on the speed of the conveyor belt. We had seen something very similar for the paper machine. In the paper machine you have also transport of material, fibers, from the head box to the scanner, right? You have a distance that has to be covered, and depending on the speed, well, the delay will be different. So here, this is a good example of a non-linear system that will behave differently according to the working point. And the working point here is influenced by the speed, in this case of the conveyor belt, and for the paper machine by the speed of the production line. Here you can see things visually. W2 is a delayed version of W1. You can clearly see that there is no amplification or attenuation, right? There is just a phase shift. Well, as we have seen, dead time is throughput dependent. It depends on speed, but it can also depend on a flow. Causes are transport. I've already talked about the transport of material in the paper machine, but also a bad location of the measurement can introduce delay. For instance, a sensor can add delay, and of course when you're sampling the system there is a delay that is due to the zero order halt mechanism. In this course here we'll assume that TS is sufficiently small that this zero order halt mechanism has very little influence. The succession of several time constants has also the effect of a dead time. We speak of an apparent dead time. So let us have a look at that. We take several first order systems in series. So let's just take 3, and we will look at the step response, right? So at the input we apply a step, and then we're going to have a look at this step response. We can have a look at the output here of the first order system. So the response will look like this. So this is the typical response of a first order system. At the output of the second first order system it will look like this. This is the response of a second order system, and at the output of the third first order system it will look like this, right? So you can see that the succession of several first order systems introduces kind of a delay over here. We speak of an apparent dead time. Process delay plays an important role in the choice of the control scheme and the algorithm. We'll review or view for the Smith predictor a mechanism that will kind of recycle the PID controller and make sure that the dead time in the system is compensated. And this is a review. We'll also have a look at the internal model controller that can also be used for processes with delay. It has also an impact on the optimization of the controller. If the ratio dead time over main time constant increases, well, it will become more and more challenging, for instance, to tune a PID controller. Dead time has a destabilizing effect, right? And this is why you need some phase margin, right, to be robust against changes in the dead time. And for instance, in the Smith predictor, you'll need an estimation of this dead time, and misestimation estimating the dead time will cause problems. So with the Smith predictor, if the dead time is misestimated, you'll probably do worse than without Smith predictor. There's an example that you can use to easily explain that a dead time has a destabilizing effect. So it's the example of the shower in a camping, and this is the shower spray hose, and you have of course two knobs that you can use to control the temperature of the water. And then in a camping, what is usually happening is that you have a boiler, right, that is situated very far away, and we speak of more than 100 meters, right? So if you're in the shower and you act as an aggressive controller, what you will do is, well, kind of ask for a flow of warm water, but since you're located so far from the boiler, nothing will happen for a while. And what you'll do is, well, turn this one open to 100%. Then after a while, of course, what will happen is that the warm water is there, and then you get burnt. So what you do is close this one to 0% and, well, start opening this one. And then of course, after some delay, what happens is that the water gets very cold, right? So this is typically what happens if you use an aggressive controller on a process with a dead time that is large with respect to the time constants. You will see oscillation in the system. Well, a delay in the time domain is really PV is equal to mv t minus theta, and if you go to the Laplace domain, right, this is what you obtain. Remember, to have an idea of the frequency response, what we need to do is take P of S, evaluated at S is equal to j omega, and then take the module. So this is the module of P of j omega, and this will be used in the top part of the body diagram. And then you need the argument of P of j omega. In our case here, the process P of S is simply exponential of minus ts. So if we replace this by S is equal to j omega, this is what we obtain, right? Exponential of minus theta, I'll put the j in front, theta omega. And this here is in polar form, so you can clearly see that in this case we have a 1 over here, so the magnitude is 1, and the argument can simply be read, it's minus omega theta. Okay, so there is no need to do a calculation like this because this is obvious, right? You simply take the transfer function, replace S by j omega, and you can immediately see that the module of the gain is 1 and the argument is minus omega theta. Observe that in the previous formula the phase is expressed in radians. This is important. Well, this is the frequency response for this process delay or dead time. We had seen that the module was 1, right, and the argument of P of j omega is simply minus omega theta, right? So you can see here that there is no influence of frequency, and if you use dBs, of course, you have here that the magnitude plot, in the body plot, is equally 0 at all frequencies, right? Here we see that the phase shift is increasing with frequency, so you have a linear dependence on omega, but remember here that we have here the log frequencies, so we can see here that we have this exponential behavior. Okay, you can see that you have a phase shift of 1 radian where omega theta is equal to 1, right? So this is 1 radian and this is approximately 57 degrees, right? So where omega is 1 over theta, we have a phase shift of 57 degrees. That's 1 radian. Here we have theta is equal to 1. 1 over theta is therefore at 1 radian per second, and we can see that indeed here we have a phase shift of minus 57 degrees, which is, and this is approximate here, and this is 1 radian. Well, we have seen in the previous section that an integrating process can be described by a transfer function h of s with an s at the denominator, and we'll give it here a gain kp. Here we have an output flow, but assume here now first that there is no output, that there is just an input flow, right? And this is mv, right? What you can do is take an mv that is positive and look at the output level, right? And you will see that the level is increasing, right? So that you have will kp mv t at the output. So if you can compute the slope, we will call this the slope, right? Well, then kp can be determined simply by taking the slope that you observe and divide it by mv, right? Here the situation is a little bit different. We have an output flow, right? And we will assume that it is unknown, right? And what we'll do is do a manipulated value change. So we'll start with an mv, and apparently this mv is such that the output flow is larger than the input flow. As you can see, the level is decreasing, and after our step we can see now that the level is increasing, and this is telling us simply that now in this second situation, well, the input flow is larger than the output flow. In this slide we have the same situation as before, but we have added a delay, and as you can see, the delay can really be determined rather easily. You can see that after we have had the change of mv, well, it takes a delay of theta before you can observe the change of slope. So remember that we have a process here that is integrating. It will have gain kp, and it is an integrating process, right? And what we want to do is to determine kp, and we have done this experiment on this, well, integrating process where we had this unknown output flow, and we want to determine kp. So what you need to do is to compute the slopes before this the manipulated value change and after. How do you compute the slope? Well, you set a set period, delta t1, and you look at the change in delta pv, right? So slope 1 is delta pv1 over delta t1. You do something similar to compute the slope after the manipulated value change, and you'll obtain this slope 2 and slope 1 experimentally. We have here our process in the Laplace domain, and it's Kp over S, right? And in the time domain you can write it like this. Note that for such a process, if mv is equal to 0, when then PV is constant, right? If mv is positive, then PV will be growing linearly, right? And if it's negative, PV will be decreasing, right? Here we have a constant mv, so the output will be Kp times this constant time t, right? So what we see over here is the slope, right? And we have determined this slope experimentally. And what you see over here is the slope for the second operating point mv2, and we have also determined this slope experimentally as follows. So we have here that Kp mv1 is this slope that we have determined experimentally, and we have something similar for Kp mv2. If we subtract both equations, this is what you obtain, and you can see here now that you can obtain Kp experimentally from this experiment that is shown in the previous slide, and this is done independently of f out. Of course, f out has to be constant. Assuming that we are working in a normalized fashion and that we are at steady state, we can write PVN, and for normalized is Kpn mvn times t. We'll assume that mvn is constant, right? It is expressed in percent. We are at steady state, so the output will grow linearly. The output is also expressed in percent since it is normalized, and you can see here that this is growing. This has units time, so this one must have units 1 over seconds, right? So this is why Kp is often written as 1 over a time constant, when Kp is, the gain of an integrator, and this will be the case in the section on PID control. The integral action, right, will be 1 over Ti, the integral of the control error, right? And you can see here that the gain of the integral action has been written as 1 over a time constant. Well, we have just seen how you can obtain the gain of the integrating process experimentally, but very often you do not need to do experimenting. For instance, the level of the tank is linked to the input flow by integrating system, and the gain is 1 over the section of the tank. For instance, the voltage on a capacitor is linked to the current by an integrating process, and the gain is 1 over the capacity, right? And you could add, for instance, that the current through an inductor is linked to the voltage by an integrating process, and the gain is 1 over the inductance. Coming back to this example of the level in a tank, if the tank is lying on its side, then things look like this, right? And the relation between the level and the input flow F in becomes non-linearly, because you can see here that depending on the height depending on the level in the tank, this tank section will vary. So we have a non-linear behavior, and according to the working point, the dynamic behavior will be different. The working point will be determined here by the level in the tank, and you'll have something very similar if you have a conical tank. So for instance, in this region over here below this line, the level, the relation between level and input flow will be non-linear, as the section is changing all the time. When you're above this line, of course, things become linear again, and then you have the standard integrating process again. We can now have a look at the frequency response of this integrating system. Remember that we have to take P of S, evaluate at S is equal to j omega, and then take the module and the argument. In our case, we'll have Kp over j omega. The module will be Kp over omega, and the argument of P of j omega, because of this 1 over j here, is minus 90 degrees, and this is clearly observed here in the phase body diagram, right? So now we have to look at the module. You can see that this module is evolving as 1 over omega, but in a log frequency body plot, this looks like it is evolving linearly, right? And the slope here is minus 20 dB per decade. Where is this coming from? Well, we are working in dB, so what we have to do is to take 20 log 10, and what I'll do is look at what happens when I multiply the frequency by 10. So we'll have Kp divided by 10 times omega, and we'll use this formula that log of A times B is the log of A plus the log of B, and this is true in any base, so also in base 10. What we'll have here is 20 log 10 of Kp over omega. So this will be the gain here at the frequency omega expressed in dB, and here you'll have plus 20 log 10 of 1 over 10, right? So this one will be minus 1 times 20, so this is minus 20 dB. So what you have to do to obtain the gain expressed in dB at 10 times omega, well, you have to take the value in omega and will decrease this value by minus 20 dB. So indeed here you have a slope of minus 20 dB per decade. Well, another important fact is that you can determine the gain by just looking at this body diagram. The frequency at which Kp omega is equal to 1 is, of course, omega is equal to 1 over Kp, right? In our case, Kp is equal to 1, so the frequency at which we'll have a gain of 1, which corresponds to 0 dB, is indeed here at the frequency of 1 radians per second. This is more intuitive than you think. If you take an integrating process, 1 over S, and at the input you apply cosine omega 0 t, assuming that you're at steady state, what will come out here, if you integrate this cosine, is the sine of omega 0 t divided by omega 0, right? And the sine is really a cosine that has been shifted by minus 90 degrees. So this is what you see over here. The gain is 1 over omega 0. The smaller the frequency, the higher the gain. And this is also what you see here in this body diagram. Let us look at the following loop. So we have an integrator, kp over s, and this very simple loop with a minus and a plus over here, right? And we'll put a 5 at the input over here, and we'll ask the question, what are the values in steady state? Well, the only steady state that is possible is to have a 0 over here. If we have something positive, it will be integrated and it will evolve, so it's not steady state anymore. So if we have a 0 over here, it means that we have a 5 and a 5 over here. So here you can clearly see that in steady state the gain is infinite, and this is indeed what you see here in the body diagram. And when you encounter a process where you have an input that is 0 and an output that is finite and non-zero, well, this means that there is an integrator in this process to cause this effect, and this integrator will cause an infinite static gain.